at the end of our first part then of statics, we get two results. The first is a global statement of equilibrium, and then the other one is a bar level or a segment level. I'll go ahead and call it the bar force. So by the bar force, we mean we have an expression for, for P1, P2, and P3. And the nice thing about these is they are all in terms of the single reaction RB. This one was in terms of both RB and RE, are both of our reactions. But at the end of the segment, the way that we've constructed it, if we draw that bar force and look at the left-hand side, they're all in terms of RB. The second tool that we have of our big three then is going to be the stress-strain law. And the stress-strain law manifests itself as delta is equal to PL over AE. And our goal in this step is effectively to calculate the bar stretch for each segment. So we will compute the bar, I'll put stretch in quotes, for each segment. Now, why am I saying stretch? It might shrink for each segment as well. I'm going to break out the eraser a couple of times today. Why am I saying bar stretch? Well, because we've assumed that each of our bar segments is in tension. So that is the assumed sign. So there is an assumed stretch. Clearly, some of these bar segments are going to be stretching, others are going to be contracting. So when we say stretch, we might realize that some of the stretch segments will be negative or contraction. We do that then just by using deltas PL over A for each P. So for example, in this one, we have three. We have three segments for our little example that we're going through. The first is we would write the delta of B to C. So that means how much is bar BC stretching? Now in this case, that also happens to be equal to the delta of C relative to B. And in this case, B is not moving. But I think it's okay if you just use these two subscripts. So this is the bar stretch in the first segment, BC. And what is that? Well, it's going to be the force in bar segment 1 times the length divided by its area and its modulus elasticity. Now here, notice it's the 1, not the parentheses 1. We just mean the first chunk because we have actually two materials, right? We've got the one like this and then the one like this. And by 1, we mean this guy. That's the second and that's the third. So if we had the parentheses around it, that's material 1 and material 2. Sorry about that. So in this case, we know that P1 is RB. L1 is 6 inches. The area is equal to 4 square inches, and then the E is 20,000 KSI. Incidentally, as soon as we do that, as soon as we write in the E values as KSI, then we realize that RB must have units of kips. So RB is going to be in terms of kips. Again, why is that? Because we have to have something cancel out for the E value to be consistent. That means that RB is going to be in terms of kips. We'll also have then delta of C to D. So that's going to be the force in bar 2, the length of the second segment, area, and the E value. Now again, the 2 means this segment, which is the same as properties of 1. We're just numbering those in ad hoc fashion to denote the fact that we've got 3 segments. That's going to be RB minus 10. That is the internal bar force for the second segment, times its length, that's 4 inches, divided by the area and the 20,000. Notice that these lengths are only for those segments of bar. It's only for the length from B to C, only for the length from C to D. A lot of students, for one reason or another, they want to put the total length to the left that they did in the free body diagram. Don't do that. So the lengths that we use, note, L1, L2, and L3 are for that segment only. because what you're doing is finding the bar stretch in that segment. So it doesn't make sense for you to include length that is outside the domain of that particular piece. Then finally, we have the delta of DE, total bar stretch in segment 3. That's the third segment, internal force times its length, area, and the E value. So that'll be RB minus 6. Its length then is 8 inches. And then its area is 1.5 square inches, and its E is 10,000 KSI. So at the end of that particular operation then, we have 3 more expressions that relate the displacements in each bar segment to the reaction at the left-hand end. So it almost looks overwhelming at this point. We have so many statements, but it's going to turn out to compress extremely quickly. So now we'll go to our last tool of solid mechanics, and that's going to be compatibility. I'm going to abbreviate that. Now, here is how we're going to characterize this particular representation. It's the easiest way, I think, to do it. We've assumed that there is stretch in bar 1, bar 2, and bar 3. But we also know that the total bar doesn't change in length. So we're going to write this as delta 1, or I'll write it as delta BC, plus delta CD, plus delta DE. Stretch in bar 1, plus a stretch in bar 2, plus a stretch in bar 3 is all going to be total bar stretch. And that's going to be equal to 0. So that's going to be our statement of compatibility. So for the fixed bar, compatibility says that the total stretch in the bar is going to be equal to 0. This is slightly different than the formulation that we did originally. Remember when we first started talking about this, and we said we have these 2 segments? Then we said that there can't be any gaps or voids in that segment. And that's basically going to be embedded inside of the way that we've done this, because what we would say is a stretch in that bar plus a stretch in that bar is 0. What that means is stretch in that bar is the compression that we've got in that bar. So we have the 2 bar segments that one is shrink, one is stretch, and that's going to be embedded if we just stick with that particular way of formulating things. Now notice what happens. Every one of those, here is delta of BC. Delta BC is there. Delta CD is here. Delta DE is here. We're going to add all those up, and you see what happens? The only unknown in there is RB. So let's draw this off to the side. We are going to have as our statement of compatibility RB times 6 divided by 4, 20,000 plus RB minus 10 times its length, which is 4, divided by 4, 20,000 plus the last one, which is RB minus 6, times its length, which is 8, divided by its area, 1.5, and its modulus elasticity, which is 10,000. And all that is going to be equal to 0. So there we have it. We have, by taking our results from the stress-strain law and putting it into our statement of compatibility, we've boiled this down to one equation and one unknown. And incidentally, a lot of times what's going to happen is some of these terms are going to cancel. For example, if I add this all up, I can cross out those 3 zeros because that 1,000 factor is common to everything. Sometimes it'll be a little bit easier, sometimes it won't be easier, but frequently we will get some terms that cancel. We'll try to kind of point that out. Now this, you may look at that and think, what am I supposed to do with that? Well, it's easier than it looks like, because notice you're going to have something times RB plus something else is all equal to 0. So this goes to the other side. You divide through, and you're going to be able to find RB. So everything hinges on the reaction RB. So that's pretty easy. I think you'll be able to do that. So we solve for the reaction at the left-hand end. And that is going to drive all other results. So then we would say it is off to the races, ... Why is that? Well, because then the stress in the first segment, the first bar, is going to be P1 divided by its area. That was the 4. And P1 is just RB. RB divided by 4. Sigma 2 was equal to P2 divided by 4. That was RB minus 10, all divided by its area. And then sigma 3 is going to be the P3 divided by 1.5, and that would be RB minus 6 divided by 1.5. Now, the signs are all going to come out on this. So if these are positive, they're going to be in tension. If they turn out to be negative, then they're going to be in compression. So we have to give the sign on the stresses. So make sure you do that. So if RB turns out to be 5, then bar 1 is in, that's a 5. That will be in tension. That's going to be in compression. 5 minus 6, that's going to be in compression, and so on. So we calculate the stresses after we've got that first reaction. Notice we've never had to find RE at this stage. Notice we did not need yet R sub E. Now we obviously want it. We want to know what that end reaction is, but we don't need it to solve what remains of our problem. Okay, so at the end of, after we found RB, we can get the stresses. We also need the displacements, but since we're closing in on 12.5, let's go ahead and end the second part of our lecture now.